Okay, off we go. So a real quick announcement, reminder announcement. Attendance code. Make sure to get that attendance quiz put in. Remember, it disappears 2 minutes after the start of class. And to be more precise, you cannot submit after 2 minutes after the start of class. So you got to get it. It's not enough to open it before the 2 minute mark. You got to get it submitted. Also, don't forget to check and make sure that your score is recorded. Make sure that you get credit for the score. It's part of the process. Okay. All right. So here's where we left off. We were talking about graphs and level sets and stuff like that, right? And I've spent a lot of time emphasizing how they are very, very importantly different, right? You cannot apply the calculus of graphs to level sets and vice versa. Okay, we've already seen one connection. Level sets, in some reasonable sense, are horizontal cross sections of graphs. There's a nice relationship between them. And here's another one. It all turns on this algebra right here. Look how trivial. Practically nothing happened. Right? All I did is I took the right side and I subtracted it over the left. How could this possibly be useful? Well, it's useful as follows. Notice that what I started with is a graph. And what I ended with is a level set. Right? So, trivial though it appears to be, this is a way of taking what might come to you as a graph and turning it into what you can now interpret as a level set. And so, if, for example, if you need to use the calculus of level sets at some point, now, we don't know what that is yet, but surely you'll trust that at some point we will develop some calculus ideas that'll geometrically make sense in the context of level sets. If you need to use any of the calculus of level sets, but what you have came to you as a graph, boom, do this. No problem, right? Now, a sticky wicket, common source of confusion and mistakes. The function whose graph you were looking at is not the same function as the function whose level set you turn that into. These are different functions, right? Again, I cannot emphasize enough, graphs and level sets are not the same thing, right? So it would be silly for me to think that these two functions should be the same function. You can interpret any graph of a function as a level set of the same function. Nonsense, right? So this is a different function. Y is an input variable for this new function. It was not an input variable for the original, for the original function. And that little detail really, really matters quite a bit. Okay, so let's see an example of sorts of this, and here we go. So here is a function, and we're going to look at the graph of that function. Here it is. Here's the graph of that function. And okay, if I wanted to play calculus of level set games, what's the function whose level set relates to the graph that I'm actually interested in? Well, you notice we do this just exactly the algebra above. So easy. Trivial. Barely worth mentioning. Right? And what we see now is that, yes, we can view it as a level set. And this is the new function. That's the function g, to which you can apply the calculus of level sets and infer conclusions about what this level set looks like. That is, what the original graph looks like. Does that make sense to everybody? Okay, real nice little trick, very useful in lots of circumstances. Unfortunately, this is a one-way trick. Every graph is a level set, but not the other way around. Not every level set is a graph. Easy counterexample. Right, here's a level set. Right, I got something set equal to a constant. Clearly a level set. It's not the graph of anything. If it were a graph, I would be able to represent the entire thing by writing y equals and then having a function, right? And of course we can't do that. Now you may be thinking, yeah, what about, plus, minus, square root? Okay, well that's not a function, right? A function is only allowed to have a single value per, whatever inputs you put in. Okay, so, yeah, it's a one-way deal. All right. moving along. So, yeah, there's a couple of neat tricks I want to show y'all about how to understand equations of three variables, or you might say equations in three dimensions. How do you draw pictures of these things, and, you know, if you just need to know what it looks like. So, this is another tools for your toolbox kind of a deal. There is no single algorithmic, you know, toss it in the hopper and turn the crank 3 times. There is no such thing. Right? But I'm going to show you a couple of tools that I think are really nice. I think these are underappreciated, frankly, but very clever. Really useful ideas. Here's the first one. Sometimes you will see an equation that has this property. It may have x's and y's in it, but they appear only, that's very important, only as part of this expression right there, square root of x squared plus y squared. No other extraneous x's or random unaccompanied y's. X and y appear only in that form. Now, again, common scenario, as it turns out. I'm going to show you several examples. When that happens, and by the way, let's take a quick moment to recognize how easy it is to notice. Right? X squared plus y squared, there it is. Not hard to notice it, right? So this is a low-cost theorem. Eyeball glance. And what you get out of the deal is that is rotationally symmetric around the z-axis. Now that is a lot of geometric information, right? Rotational symmetry is, well, it's a tremendously strong property. The overwhelming majority of surfaces are not rotationally symmetric, and knowing that yours is very helpful. Okay, so let's see why this is true. A couple different ways to think about this. I'm going to start off by observing that if you have some point, whatever, any point, and if you then rotate that point around the z-axis, and let's look at a particular second point that you get by rotating like that. And of course, we're assuming that our equation satisfies the condition there that x and y appear only in that special form. Here's the thing about those 2 points. Now, they're different points. They have different x's, they have different y's. Most of the time, when you have 2 different points with different x's and different y's, and you plug them into some equation, you're putting different numbers in, you would not expect any relationship between how those equations either work together or don't work together. Who knows? Here's the thing. If x and y appear only as part of that form, and notice that is exactly the distance from the z-axis, aka it's our cylindrical r. These 2 points have the same value in terms of every way that x and y show up in the equation. And another nice thing about rotations, preserve z. If you're rotating around the z-axis, these 2 points have the same z. So as far as what you put into the equation is concerned, these 2 points behave the same, simply by knowing that they satisfy that property. And so either these 2 points, they either both work or neither of them works, but they always agree. And if you think about it, then that means that the set in question has to be rotationally symmetric. So it's a really nice little observation. Let me show you a different take. Same conclusion. Another nice way to think about it is to just think about what the cylindrical equation would look like. Now let's just think that through for a second. The cylindrical equation. Okay, well, we take our rectangular equation, we start plugging in formulas, and x is our cosine theta, and y is our sine theta. And you can see you're going to, every time you have an x and every time you have a y, you're going to have r's and thetas showing up. Except if x and y appear only as part of that special form, and we've already agreed that special form will turn into exactly r, then you're not going to have any thetas showing up in the equation. Every time a theta shows up, it'll be part of a little Pythagorean identity, and it disappears. So the condition as I've written it is equivalent to saying that the cylindrical equation has no thetas in it. And we've already talked about that, right? If a cylindrical equation, if the thetas don't show up, then all the cross sections look the same, and so therefore it's got to be rotationally symmetric. So take your pick. I think these are both really good arguments. Either way, we get the desired punchline. So why do we care about this? How does this help us? Well, here's the interpretation that's going to pay off. When you have this rotational symmetry, now this is going to be a geometric appeal, right? You have to kind of think about what this looks like. Look at its cross section in any plane that contains the axis. Doesn't matter what plane, any plane at all that contains the axis. If it's rotationally symmetric, you can look at that cross section and just rotate the cross section, and that will produce your surface. Now, again, purely geometric appeal. Does that seem like a plausible suggestion? Okay, so let's see this in action. It's a really cool example. By the way, you'll recognize this equation. So I threw this equation in there at some point. We were talking about horizontal cross sections of graphs being level sets, and I wanted to use this equation here. And I apologized for the fact that, well, we don't really have the tools to figure out what this thing looks like yet, and now we do. Let's figure out what this thing looks like. Notice x and y appear only in the special form. And so this thing, whatever it is, this thing is rotationally, I keep missing it's rotationally symmetric around the z-axis. Powerful, powerful conclusion. Because now I can say, all right, I'm going to pick any plane I like. I am feeling like picking the YZ plane, whatever. Pick any plane that I want that contains that axis. Let's figure out what the cross-section looks like. Still don't know what the surface looks like, but we can figure out what the cross-section looks like, because in this plane, I know that x equals 0, and if I plug in x equals 0 into there, this equation turns into that which we immediately can see is a parabola. Is that cool? I mean, it's all over but the shouting. We know it's rotationally symmetric. We know that means we can produce it by rotating any cross-section, and we have found one of the cross-sections. And so take this orange curve here, parabola of course, and just imagine now what happens when you rotate that around the z-axis, and what you get is a bowl-like shape like that, just like we discussed last time. And this is how you see what it is. How are we doing? Is everybody happy? Okay. Really nice method. Really powerful. Now, a common question that I get at a time like this is, how did I know to use the YZ plane? Answer, it doesn't matter. Pick any plane you like, as long as it contains the axis of rotation, so z-axis here. So let's see how it plays when you choose a different plane. So now again, we'll start the same way, looking at this equation. X and y appear only in the special form. Oh, hey, you know what? Let me just, some of you may be wondering, hey, why is there no square root in there? Let me just observe. I can rewrite this as square root of x squared plus y squared squared. Right, so even though it technically, it doesn't, the way it's written, it doesn't look like it's got that square root in it. It does. Okay, so rotationally symmetric. Let's observe. This gives me that, namely, that's the axis of rotation. I feel like I can do better than that. And now let's pick a different plane. Right, in the last example, I used the YZ plane just to show that I can. This time, I'm going to use the XZ plane, otherwise known as y equals 0. And let's see what that looks like. The equation turns into this. Again, flashbacks to high school. right? This is a hyperbola. It's a hyperbola that looks like this. Now, real quick, I'm going to interject. I know a lot of y'all, it's been a while since Algebra 2 or whatever they call it these days. It is important that you be able to distinguish this hyperbola from the one that kind of, goes the other way, right? So you got to make sure you, let's say, orient it the correct way, right? It's easy to mess that up if you're not death grip sure that you know how to do that. Come talk to me, right? I'll be very happy to show you a couple of easy observations that you can make that'll make sure that you get this right every time. Okay. Anyway, old high school stuff. So there's the hyperbola, and again, game over. It's all over with the shouting. It's rotationally symmetric. Here's a cross section. I just have to use my geometric intuition. What happens when I rotate this orange curve around the z-axis? And it is something like this. I think that's a pretty reasonably satisfying geometric assertion there. Is everybody good? Okay. Why X and Y? Right? Why was I thinking about X and Y and concluding that it's symmetric around the Z-axis? Why haven't we entertained if Y and Z show up only in an analogous special form, and then would that mean it's rotationally symmetric around the X-axis? And the answer is absolutely. Yeah, totally. So there's a total of 3 of these theorems. There's the X version, the Y version, and the Z version, if you will. So we kind of started with what you might call the Z version. So the arguments are pretty much the same. I think this is a fabulous opportunity for y'all to think through the details. Don't just do a find and replace, on, everywhere you see an X, you put a Y, or whatever, right? Think through the argument. Think through how would you interpret this expression if it was Y and Z instead of X and Y? How does that change the picture? And just think through the details. It totally works, and you get 2 new theorems. Let's apply one of these new theorems. Let's look at this equation. Now, at first glance, you might think, okay, let's look at the X and Y. I see an X squared, I see a Y squared. There's minus signs, but we can massage the minus signs, and let's start moving things around and use parentheses, and it doesn't work. You can't write this with X and Y appearing only in the special form. It just doesn't work. But what you can do is rewrite it in such a way that Y and Z appear only in the special form. So this is rotationally symmetric around the X-axis. Everybody buy it? Okay, so rotationally symmetric around the X-axis. I like to draw the axis of symmetry just to help me, I find it comforting or something, right? It helps me visually see what's going on. Now again, pick your favorite plane that contains that X-axis, whatever. By the way, you don't even have to pick a coordinate plane. If you want to pick, like, Z equals Y, technically you can make an argument there as well. Now, it'd be a harder argument, and there'd be some geometric issues and sort of distortion effects of how the coordinates are not exactly the same as the distances, and it'd get a little weird, right? So I don't actually recommend that, but technically you could make such an argument work. All right, so I'm going to keep it simple. Pick a coordinate plane. Arbitrarily, I'm going to take the XY plane, otherwise known as Z equals 0, which I can plug into there, doing which makes my algebra turn into that. Again, with the hyperbola. Again, you got to make sure you get it sort of going the correct direction. Make sure you get that right. Come talk to me if you're not sure. And now again, it's all over with the shouting. I just have to visualize now what happens when I take this thing and I rotate it around my axis of symmetry. And it's artistically hard, unfortunately. But it looks, it looks kind of like that. It is just a hard surface to draw, Sometimes they're just hard, and my advice when you're trying to draw something that is really hard is do your best and accept imperfection as unavoidable. That's how drawing works in some cases. So you're just not going to be able to... I have not been able to figure out how to do a better job than this, and I'm not happy with this. Okay. All right, so basically the same idea. How are we doing? Is everybody with me? Now, a little terminology. In both this case and this case, we're looking at the result of rotating a hyperbola. And so in both cases, we call them hyperboloids. But nevertheless, this surface does look different from that surface. And this one has one connected component. This one has two connected components. And so the terminology is hyperboloid of one sheet. And this is hyperboloid of two sheets. Yeah. Anyway, just lingo. Okay. All right, so be on the lookout. You're going to, more often than you would expect, find yourself looking at equations where, this might look kind of weird at first glance, but where if you look carefully and you think about it, maybe a pair of variables shows up only in this special form, and then you've got a massive, powerful tool to be able to work with. Okay, next. So deformations. This is a weird one, a little bit of a weird one, but I'm going to start with a surface that we know what it looks like. Nice, easy surface here. Now, how do I know what that looks like? Well, you got a couple of options for how to interpret this. I can convert this into spherical coordinates without too much trouble. Rho equals 13. Sphere of radius 13. If I hadn't noticed that, I could argue that x and y appear only in the special form, and therefore this is rotationally symmetric around the z-axis, and I could play that game. And again, you'll get that it's a sphere. Take your pick. So we have an equation, and we know what it looks like. Okay. Here's the question I want to ask now. What would happen if I tweak this equation? How would that tweak the picture? Now, specifically, let's suppose that the tweak I'm going to do is everywhere I see a z, I'm going to replace it with a 2z. What happens? Right? We tweak the algebra, and you think that would then correspondingly tweak the geometry. How so? Okay, well, let's think about this equation here. What can I say about that equation? I've got some points over here that worked already. Let's see, I'll use orange, I guess. So I've got this point, 3, 4, 12. That works in that equation. Easily checked. A little bit of arithmetic. Fun example, by the way, of what's called a Pythagorean quadruple. Right? Y'all seen Pythagorean triples? 3, 4, 5? Right? This is a Pythagorean quadruple. I like nice round numbers when I can. Does that point work in this equation? Of course not. I tweaked the equation. It's a different equation. The numbers are all out of whack. Right? But the clever move that you can make, the clever observation that you can make is that while that point doesn't, this point does. In some sense, you can sort of notice that, hey, what I had been using as z, I'm going to have to multiply that by 2. So let's divide by 2 in advance. And then when I have to multiply by 2, now I'm back to the 12 that I had before that made all the rest of the arithmetic work out, and we win. There's a little clever little smart alecky observation. Right? So every point on this green surface, by this little trick, I can produce what you might call a corresponding point on this light blue surface. And the whole process, the whole trick of how to produce the corresponding point, divide the z-coordinate by 2. So punchline, this process, let me get rid of the mess. The process that happens geometrically is that the surface gets squished in the z direction by a factor of 2. Is that cool? It's a nice little punchline, by the way, and again, category of questions that mathematicians really like. Hey, what's the relationship between algebra and geometry, and what's the relationship in this case between this little algebraic tweak, and what is the resulting corresponding geometric tweak? And this is a nice, crisp answer. In some sense, whatever you do to a variable in the equation, in some sense, kind of the opposite happens to the geometric figure. So this is a nice sort of general rule of thumb. In some sense, you're undoing in advance what you know is in some sense, what we've done in the algebra, we know we have to undo in advance to account for what we did to the algebra. And so thus this idea of the opposite happening. Okay, so the example that I've showed you here is about replacing z with a constant times z, but you could imagine analogous arguments. What if I divided instead of multiplying? Well, then instead of squishing, I'd be stretching. What if I replace z with z plus a constant? Well, then you would just need to subtract that constant from all the z coordinates. And so that will translate your surface. Shift it, up, or I guess down. So it'll translate it downward. So, et cetera, et cetera. And all the arguments are totally analogous to what we see in this example here. So, a couple of real quick examples. Let's ask, what does this thing look like? And right off the bat, I don't know. And I do see there's an x squared, and I do see there's a y squared, et cetera, and you might be tempted to try to make some argument about rotations, and the problem is these a's and b's presumably are different. We can't assume they're the same anyway. And so, no, x and y do not appear only in the special form. So I got nothing. I'm out of business. I have nothing I can do, it would seem. Certainly not with rotations. But what you can do is say, you know what, this one I already understand. That one's easy. Rotation argument works just great, or spherical coordinates, or probably other points of view. Take your pick. And then I just observe. All I did between these two equations is I did, for example, a tweak. I replaced x with x over a. And the result then is going to be that this picture is just stretched in the x direction by a factor of a. And then likewise for the y, right, you can see we're doing that in the y direction, so that'll stretch by a factor of b in the y direction, and likewise analogously in the z direction. Everybody cool? It's a really nice argument, really clever. We started with something that's not nice. I noticed that it's just sort of a tweaked version of something that is nice, and then we accommodate for the tweaks. Yeah?
So you talked about how, on the right, x and y are in special form, but
right.
you interpret it as you're just multiplying each by 1 over a and 1 over b.
That's, I feel like, exactly what we did, yeah.
Yeah, so
yeah.
Why can't you interpret it as being the special form?
Oh, because it's when we say the special form, that's a very strict form, right? If you look back at the formula we wrote down, it's got to be square root of x squared plus y squared exactly, because that's distance, right? And the way that the argument works is presuming that we're talking about points that are rotations of each other, and when you rotate, it's literally the distance to the corresponding axis that we have to talk about as being the same.
Okay.
So it's very strict. It's got to be exactly that form.
So on the left, if you were to scroll back down.
Yeah.
So on the left, it is in that form.
On the left, it is in that. Yeah, that's right. So we can make. So there are 3 different rotation arguments we can make here, right? Take your pick. Easy money, right? Even though we couldn't make the rotation arguments here, in some sense, we change the problem, we answer the problem where it's easier, and then we account for how we change the problem.
Okay.
Yeah. Yep. Okay. Good stuff. Okay, now one little algebraic warning. The various details here, you can read through the rest of the details. The book has some examples, but there is a very commonly stepped on landmine here. Let's look at this first example. A lot of students will see this and think, oh, looks like I've replaced x with x over a squared. That's sort of cosmetically. Right, if you just look at the symbols and forget about what they mean, it kind of looks, you can see where a student might, you see what I'm saying? I mean, kind of tempting, right? It doesn't work. This doesn't make any sense because you see x gets squared. And so when I say replace x, what I mean is replace x and then do exactly to that what we had previously done to x. And let's see here. We are not, let me put a big X through this because I'm about to write down something that's not true. It's not x over a squared that gets squared. It just isn't, right? So got to be careful about this. What it is x over a. That's the thing that gets squared. So the substitution here is that x gets replaced with x over a. Everybody happy with that? Real easy to mess that up. Think it through, right? Be careful. Otherwise your stretching factor is going to be wrong. Okay, likewise this example down here, again, other examples in the book. Okay, we're done with 2.1. Then move on to 2.3. By the way, we're skipping section 2.2. I'm sure you've noticed. 2.2 is about limits. It's very, very cool math. It's very important math. It's historically important math. There's a lot of, so much mathematically interesting and historically interesting stuff to say about it. And unfortunately, it's a lot to say. It's a big topic, and it's not really quite what this course is about. So if this were Math222, I'd be dwelling on it, because this is not that course. We're looking for more sort of like functionally, let's just kind of get it done. You know, how do we solve problems? How do we have intuition? What does it look like? How do I work with it? Right? That's what we're interested in this course. So limits are, I just don't think it is really quite the point. Which makes me sad, but oh well. So we're going to move on to 2.3. We're going to talk about derivatives. First thing to note, there's more than one of them. That should be an eyebrow raiser for you. Think back to single variable calculus. There's only one derivative. The derivative. That's why they call it the derivative, right? That's all there is. So in multivariable calculus, there's several of them, like 4 or 5 different kinds of derivatives, different in certain ways. And they're all kind of related to each other, connected to each other in various different ways. They are nevertheless all different. Now, I have a gripe, and that is when two things are different, shouldn't we call them by different names? Right? It'd be kind of confusing to use the same name to refer to different things. So why do we use the word derivative if they're all different? And the reason why is because they all have a common unifying feature. In their different ways, they all relate input changes to output changes. The inputs that you put into the function, the outputs that come out of the function. Every derivative we're going to talk about will relate input changes to output changes. Okay, so that's something to think about. I encourage, as we go through and talk about different kinds of derivatives, be on the lookout for how does this feature hold for that kind of a derivative. We're going to start with partial derivatives. I have very mixed feelings about this. Mostly we're going to do this because the book does. Side note, most multivariable calculus books start with partial derivatives. So there's good arguments for it. Here's a couple of them. They're familiar and they're easy. It's a nice little first step, right? We can get our feet wet a little bit. So that's cool, I suppose. The problem, and what makes me uncomfortable about this, is that when you leave this course, I hope that you are not still thinking of partial derivatives as being sort of like your cornerstone, sort of like fundamental point of view on how to think about multivariable derivatives. They're really not good for that. There is a much, much better way to think about multivariable derivatives, and it's not this. Right, so again, I think this is kind of the downside of starting with partial derivatives. There's this risk that you're going to think, okay, here's what it is, and that's what it is, and everything else is tweaks of that. And I think that's the wrong way to think about it. So anyway, heads up, don't get too comfortable with partial derivatives. Here's what they are. Here's how to compute them anyway. Let's go ahead and do that. It's a little silly. Got a multivariable function. We don't know how to deal with multivariable functions yet. Okay, so wouldn't it be nice if we could turn a multivariable function into a single variable function, because we know how to do single variable functions. Now, that's a cop-out. Right, it's ducking the question, really, kind of, right? So, but that's what this is going to do. We're going to take all of these different variables that we have, and we're going to just stick our head in the sand. We're going to pretend that they're constants. We're going to insist that they be viewed as constants, which they aren't. You should be very uncomfortable with this. This should make you, well, wait a minute, can you do that? Is that legal? Seems kind of wrong. Anyway, but we're going to do it. We're going to hold all the variables constant except for one. And now, this function that I had that had multiple variables, well, not anymore. Now I've got a function that has a single variable. I have, in fact, now a regular, good old-fashioned Calc 1 single variable function. And you can just take the regular old derivative of that resulting single variable function. That's what a partial derivative is. So, again, a little uncomfortable, little suspicious, and I'm going to come back and address that in a few minutes. By the way, here's another quickie observation, something for you to be sort of stewing on for the next few minutes. I mean, I did something really weird here. How do I know that this definition gives me something that's meaningful? Right? Maybe that just makes the whole thing crash and burn. Maybe this is nonsense. I encourage, you should be worried about this right now. I have written down something very weird and suspicious, and you should be concerned this might be meaningless garbage. It's not, right? But you should be worried about that, right? Okay, a notation we just have to write down. This is the most common notation for how to write a partial derivative. You will notice this little symbol here. It looks kind of like a D. Very importantly, it is not a D. You cannot write it as a D. That would mean something different, and it's not an alternative, and it is not acceptable, and you'll lose points, etc. Right? So it's annoying and frustrating. I'm sorry to have to make y'all deal with the tedium of here's a new symbol I've got to learn how to write, and it's humiliating to have to do this, but I did it when I was y'all's age, and I sat down with a piece of paper and I practiced how to draw that. And I decided if I was going to swirl inward or swirl outward, everybody's got to make that decision. And you sit there and you just get to where you can make it reasonably well, and you just have to do it. I'll also point out is not a lowercase Greek letter delta. And again, not acceptable, right? You can't do that either. Okay. Here's another notation where we use a subscript, the subscript indicating which variable you're going to treat as a variable. In other words, which is the one variable you're not going to hold constant. there's some times when this is a really, really convenient notation. In some sense, most of the time, I like to do it this way, but there are times you're going to see it happen when it happens that this is really nice as well. Okay. All right. By the way, one quick thing. I'm going to do a real quick comment, be very brief. Notice how this doesn't look like a fraction? Well, I mean, it's not a fraction. So maybe that's okay that it doesn't look like a fraction, right? There's something a little weird about the fact that this looks like a fraction. It's not a fraction. Really. I mean, it's kind of, you can assert certain conditions under which blah, blah, blah. But you will notice very absent from this discussion is I have not defined this thing here by itself, have I? I have not defined what partial f is. And I'm not going to because it's not a thing. By itself, that does not mean anything. So, a little uncomfortable, again, to write something with a notation that makes it look like you're dividing something by something else when those somethings aren't somethings. Right? So, pros and cons. Okay, let's do one. Again, not sure what this means. Again, I hope you're suspicious. Let's take a partial with respect to y of this monstrosity here. Yikes, right? 3 factors. One of them's a composition. It's got a cotangent in it. I never can remember which way the signs go on tangent and cotangent. It's weird. So what are we going to do about this? The big thing to remember is that when you're taking a partial derivative, all the other variables are constant. So in this case, x and y being the other variables, constants. That means that x is a constant. That means e to the x is a constant. This is a constant. That's a constant. So that's a constant. So this whole thing here is a great big ugly constant. Though, in fact, this is actually a really easy one, right? The y partial of y squared 2y, and the constants do what constants do. They come along for the ride, right? Constant factors. Done. Right? Everybody happy? So this looked like it was going to be a nightmare, and it ends up being really easy. By the way, I like to nominate partial derivatives as being the easiest derivatives to compute. To me, hands down, I think they're even easier than single variable derivatives. Because I get to just say, you know what, I'm going to call that a constant. Wouldn't that be awesome? Can you imagine if you go back to Calc 1 and you were allowed to just take entire chunks of the thing you wanted to take a derivative of and say, I'm going to treat that as a constant. That would have been nice, right? You can't do that, of course. With partial derivatives, not only can you, you must. This is awesome. Okay. All right, a couple of other quickie examples. If you're taking an x partial, well, this looks like a weird function, except for the fact that, of course, y is constant. Therefore, this exponent is constant. Therefore, just power rule. Power rule / chain rule. Old news. Nothing to it. Taking a z partial. Well, that means x is a constant and y is a constant. So this whole base is a constant. This is just constant to the power of z. And we just cite an old formula. I guess I'm using blue. Anyway, an old formula for the derivatives of exponentials. Don't forget about the base and all that jazz. Everybody all right? Okay, so now let's address the elephant in the room. How do I know this is not all just silly, nonsensical, fun and games garbage? What do these things actually look like? They've got to make some sort of geometric sense. Otherwise, it's just a weird little game we've created, right? Okay, well, important question. So the short answer is it depends on what kind of picture you're looking at. Now, y'all will remember I made a big deal out of how, hey, look, graphs are not level sets. These are different pictures, and calculus of graphs is different from the calculus of level sets. So here's example number 1. If I want to geometrically interpret a partial derivative, I want to make sense out of that calculus. What does it look like geometrically? Well, I need to know what kind of picture. Right, so we're going to start off thinking about graphs. You'll notice here what we're looking at, this surface is described as a graph. Specifically, it's a graph of this function f whose partial I want to talk about. Right? So what we're about to do is take our first steps into the multivariable calculus of graphs. Everybody on board with the context? Again, you've got to make real clear to file this correctly in your head, right? This is graphs only. Okay, so we're going to, let's see here. I'm going to take a partial derivative at this point a comma b. Right, so that tells you where you're at. We're going to take a partial derivative with respect to y. That means y is the variable that we're not going to turn into a constant. And now let's start drawing pictures. Good news, this process that we have for computing partial derivatives, hold everything else constant, take a good old regular derivative of the result. We have existing geometric interpretations of both of those steps. So we just have to basically walk through the process. Now again, we're starting at this point, a comma b. If I say x has to be held constant, because y is the only remaining variable, x started at the value a, so holding it constant means it must remain a, which means we are looking in the plane x equals a. So this is the geometric interpretation of that first step. The very first step is we're taking our graph, again, context of graphs, we're taking our graph, we're taking a vertical cross-section representing a constant value of a. Is that cool? Let me say that a little bit differently. We're taking a vertical cross-section perpendicular to the x-axis. Let me say that a little bit differently. We're taking a vertical cross-section parallel to the y-axis. Okay, cool. Now what do I get? Well, I'm going to get a curve like that, and I claim this curve as a nice property. I claim that this curve is the graph of my new single variable function. And let's think about, again, what is the new single variable function is the, when I interpret this as being a function of only y, and taking a graph of that function would mean I want height to tell me the value of the function with y being represented horizontally as the input. And check it out, that's exactly what I have, right? I have the value of the function is height, and y is representing my movement down here in the, what you might call the domain. So this is literally the graph of that new function. Okay, second step, take the good old-fashioned regular single variable derivative of that new graph. And there's nothing to it here. We already have that this is the graph, the derivative of a single variable function, derivative with respect to y, slope of the tangent line. Boom, done. That's what the partial derivative is. The partial derivative is the slope of this tangent line to this cross-section of the original graph. Let me write that all down here. Here's the takeaway. Partial derivative is the slope of the tangent line. All that sounds familiar, right? I mean, flashbacks to Calc 1, right? Slope of the tangent line. Oh my God, it's exactly the same thing. Two important little details you got to keep in mind that didn't come up in single variable calculus. One is, in single variable calculus, they don't usually bother to say of the graph, because every picture is a graph. in a Calc 1 class, right? So they just say slope of the tangent line. The only picture we ever look at, right? So make sure to emphasize to yourself, this only works for the graph. And then secondly, you got to keep in mind that it's as you're moving in the direction of the variable that you're taking the partial with respect to. So there's lots of different tangent lines. If you look back at your original surface here, I could take cross sections in lots of different directions. There'd be a bazillion different tangent lines. It is specifically the tangent line in the y direction that we're interested in here. So real quick, little last exercise. What I want you all to spend a little time thinking about, reproduce this argument and ask yourself, what does the x partial mean? It's exactly what you think. It's again, find and replace gives you the right answer, but think it through, draw the pictures, persuade yourself that actually works. Y'all have a great weekend. See you later.